This is a solution for a question covering the sublearning outcome of hydrostatic and soil loads from Mechanics 1. The question provides us with a diagram of a retaining wall and gives us that the wall is 5 meters long into the plane of the paper and is supported by an anchor rod. The soil it supports has a weight density of 1.4 metric tons per cubic meter and K is equal to 0.25. Part 1 asks, what is the greatest horizontal pressure the retained soil generates against the wall? Part 1 requires us to use the following formula where the horizontal pressure is equals to the coefficient of earth pressure multiplied by the unit weight of the soil multiplied by the total depth, otherwise shown as P equals K times gamma times H. The following values can be found from the question. K is equal to 0.25 can be found here. The unit weight of the soil is 1.4 metric tons per cubic meter, which is equivalent to 1,400 kg per meters cubed. H is the total height of the wall, which, from the diagram, is 4 meters. It must be noted that the mass density, gamma, needs to be converted to weight density as force exerted by the soil against the retaining wall is due to its weight, not just its mass. This is performed by multiplying mass density by the acceleration due to gravity, which is 9.81 meters per second squared. As a result, we get 13,734 newtons per meters cubed. The pressure can then be calculated as 0.25 times 13,734 newtons per meters cubed multiplied by 4 meters, which simplifies to 13,734 newtons per meter squared. Having knowledge that 1 newton per meter squared is equals to 1 pascal, the final answer is 13,734 pascals, which is the greatest horizontal pressure exerted by the soil, and is the final solution to part 1 of this question. Moving on to part 2, we are asked to find the force that stops the wall from overturning. This signifies we would need to form a moment equilibrium at point C, which considers two moments. The moment generated by the anchor rod, which as seen here is 3 meters away from the point of interest. The other moment is generated by the soil load through which the horizontal pressure is exerted. Therefore, our equation is as follows. The sum of moments around point C in the counterclockwise direction is equal to 0. Consequently, we have a negative moment generated by the force of the anchor rod, and this is expressed as F times 3 meters. Moving this equation to the side, our soil load needs to be calculated from the horizontal pressure found in question 1. The force is equivalent to pressure times area, where P is the horizontal pressure, 13,734 pascals, and the area of the soil load creates a triangular distribution, which means that the area can be calculated as half times space times height. We were given in the question here that the length of the wall is 5 meters long, while the total height from the diagram is 4 meters. Therefore, the total force is 13,734 pascals times half times 4 meters times 5 meters, which is 137,340 newtons. To determine the total moment, we recall from a triangle distribution that the resultant force acts at 1/3 from the base of the triangle. The total distance is therefore 4, which is the total height, times 1/3. Inputting these results to our original moment equilibrium equation, we can now rearrange for F, therefore creating a solution of 61,040 newtons, which is the force required from the anchor rod in order to stop the wall from overturning.